we just established that the gradient of the function of three variables is normal to the tangent plane that is touching the surface that's defined by those two variables and its output third variable. So if I take the gradient and I evaluate it at the point and I dot it with a vector that's defined in that plane, that those x, y, and z values will be able to help us construct the equation of the plane. So let's get to it. I have this right here, and what I need to do is I need to get all of the objects on one side of the equation before I take the gradient, because I need a function of three variables. And then I'm going to evaluate it at this point. So if I say z minus x cubed minus y cubed minus 3 equals 0, this is now my function of three variables. So I can take the gradient, and remember the gradient is the partial of f with respect to x in the I direction plus the partial with respect to y in the j direction plus the partial with respect to z in the k direction. And specifically evaluated at this point, we get negative 4i minus 2j plus k. Notice there's no z, so that 8 doesn't really come into play here. So the equation of our tangent plane is simply negative 4x minus 2 minus 2 y minus 1 plus 1 z minus 8 equals 0. And I'm fine with that kind of answer. I don't think that there's really anything wrong with that. But a lot of times people want to clean this up. So I'm going to go ahead and clean this up a little bit. We get negative 4x minus 2y plus z plus 8, 10 minus 2 is plus 2 equals 0. So if we pull that, do a little bit of algebra here, we get 4x plus 2y minus z equals 2. If we sort of added everything over and flipped it around. That's more like what you're going to see in a textbook answer or something like that. But honestly, this is perfectly fine. It kind of, in a lot of ways, helps describe what's going on pretty well. Anyway, let's move to a different problem. We have something that says f of xy equals y over x. But remember, we need things in terms of z. So the first thing we're going to do is go ahead and ascribe a z there. Then we can move everything to one side. And now we have on the left-hand side, we now have a function of three variables. So we can take the gradient of this function. So if we take the partial with respect to x, again, that's like a constant on top. So this would be like sort of like 1 over x. The derivative of 1 over x is negative 1 over x squared. But we already have a negative, so you end up with y over x squared I. And then in the j direction, we take the partial with respect to y. That's 0. The rest of this is constant. Derivative of y is 1, so it's minus 1 over xj. And that's constant in z, so the partial with respect to z is just 1. If we take the gradient at 1, 2, 2, so 2 divided by 1 squared is still 2. Negative 1 divided by 1 is just 1. And k was already, the k direction was already constant anyway. So the equation of our plane is 2x minus 1 minus, so I could say minus 1, y minus 2 plus z minus 2 equals 0. Again, I think that's a perfectly good answer, but to simplify that out, I would say 2x minus y plus z. So negative 2, positive 2 cancels. Negative 2 equals 0, or 2x minus y plus z equals 2. Again, that's kind of more like what you'd expect to see. Checking my cheat sheet here. Looks like it all checks out. It's hard to see, it's a little smudged. But ultimately, the equation of the tangent plane is simply just a matter of getting everything on one side, getting a gradient, and using the formula.